Okay, so I should probably start to talk about Lab 3. We will also, of course, also, if you're not finished with Lab 2, take questions on that today. But before, I'll just go through what Lab 3 is all about. So it is related to what we learned so far, including what we did on Thursday about transformations. If you weren't here, you should find a streaming file on that online. Okay, so let me see. First and foremost, you can go to here to the wiki, and you'll find the instructions here and the code by clicking these links. So here are the instructions. So you will recognize some of these matrices that we talked about on Thursday. And there are several tasks here, basically. First and foremost, you download the code. You set it up using CMake, like last time. And then when you run that program, you should just see a gray background. And the first task is to get up a colored triangle. So it should be something like this. So it's more or less what you've seen before, where it's covering half the screen. And you have colors associated with each vertex. Now, already in the file here, the VBO is set up, basically. And your vertex is basically now a structure with position and color data. So 2 positions, X, Y, and then 4 colors this time because you need to set this alpha channel. That's already done, basically, in this code example. And if you go down to here, you see a function that initializes the VBO, basically. And the way the data is organized this time, since you have them all in a struct, is basically the one we haven't dealt with yet on the lab, this interleaved type. So if you remember these different ways of organizing the VBOs, you could use, for example, 1 per attribute. I showed an example of that during the lecture a couple of weeks ago. The other one is that you put all the position attributes first and then the color attributes and whatever other attributes you may have. And the last one is this interleaved way, where you have the position data, then the color data for the first vertex, and the position data and the color data for the second, and so on and so forth. But this is the structure I think we have in this lab. Now, what you need to do now is to set this stride parameter. So when you set up your attributes, you have to sort of put in the things you have done before, but you also have to include this stride, which is basically the offset. Because when you tell the vertex shader to read positions, it should only read positions, right? And then when you ask it to read colors, it should only read colors. And since they are interleaved, you have to sort of skip some slots in here. So here, for example, is how you do it. So you have position data here, and then you have some other data here. And then you start, you set the starting point for position, you read these 3, and then you skip. And then you read these 3, and then you skip. And what you put in the stride, I think in the lecture I was not too exact on that issue. I think I said that you set in the number of slots you skip, but actually here you can just set the size of the whole vertex, because you know where you start, you know you're going to read 3 positions, and then you're just going to skip 1 vertex size of data and then start reading the next step and so on and so forth. The same with color, except when you start, you don't start at 0, but you start at size of the position vector, basically. Okay? So that's the first task on this lab. I don't think it's... Then the second is to start to transform this triangle. So you make this model triangle and you start to do these transformations. So first and foremost, you should map from. I can go back to the lecture there. So if you remember this drawing, here it was very difficult to see, but anyway. So you have your model, wherever it is, you map it into a world space, and then you have this camera space and the projection. So you need to set up 3 main matrices. You remember what these were? Yeah.
The scale, the view, and the projection.
Yeah, so the view and projection are two, and the scale, but in that you have three operations usually. So
yeah, translation, scaling, rotation, and translating.
yes, exactly, and in that direction. And then it goes the other way around when you multiply with your vector, right? So those are the operations you do. So you need to set up these three matrices, or actually it becomes 5 in total because you need the scaling and the rotation and the translation by itself. And then this look-at matrix, which you call it. And what did you need to feed to that look-at matrix to set it up?
This is the point of the camera.
Yes?
And the point of the object.
Yes?
And you need to subtract that.
Yep, but you also need another one to make sure that you know what is up and
I
down.
have the direction.
So basically when you have these three, you can compute this matrix. And so you need the camera position, the camera target, and the up vector. And if you remember this OpenGL coordinate system, oops, let me see. Then it's usually like that, so x, y, and z. Z positive pointing towards you. So the up vector could typically be the y-axis, right? And then in this task, you could set the target at, for example, the origin, and then the camera at some distance from that, depending. So you can maybe experiment a little bit with that as well. And of course, you have the projection matrix, where you need the field of view in degrees, or actually it's in radians. So typically you have, you should have an angle that is smaller than 180 degrees, and you should have something that is larger than 0. So around, 50, 60, 70 degrees, for example, but you have to input it in radians. And then you need the aspect ratio, which you could basically use the aspect ratio of your screen, I think. And then lastly, you would need near and far clipping plane, basically to make up this frustum thing like this. So you have a near plane and a far plane. And then it's these three matrices, which is how you move your model around in the world. And it is these scaling, rotation, and translation in that. So as you said, you multiply originally to the scaling, then you rotate, and then you translate it. And if you take a look at the vertex shader which comes along with this lab, you will see that in addition to the normal input outputs you have with the attribute set, you also have these three uniforms here. So can you imagine what they are? Yes, exactly. So you have the model matrix, which is the scale, rotate, translate, multiply together before you send it over. Then you have the U and the projection. And to address that in your program, which is which, you could take a look at, for example, this function, GL uniform matrix for FV, and then you set location here, which refers to the location in the shader. Then you have the number, which of course will be 1 here, and whether it's transposed or not, and then its values. So you can look up that function and see how to set it up and connect it up to the vertex shader. And that's one way of doing it, I think. There's also another way, as I understand. Which
more advanced.
Yeah. Okay, if you do this, then if you, for example, so you start off with the baseline here, which I already showed. Let's see if the streaming is running now. Yeah, good. And then you start, for example, move the first triangle around. So what do you do with this one? Yes? Can you see in what way you translate it? Yes, that's true.
But there's a pattern. It looks like it's moving in a sinusoid.
Yeah, that's more or less exactly what it does. Yeah. And then you add on now you do the same operations again and again and again, the same sort of triangle. And here you see the first one moving the same way, the second one is now rotating. First it's scaled, and then it's rotating around Yes, and then it's translated. So if you do this with 5 triangles, for example, you get something like this. And you see that the closer they are, the faster they rotate, right? And the more you have, the less you scale the ones in behind. But you scale them more and more, and then you rotate them faster and faster. And I think that the translation is more or less the same for all. So if you put in many ones, like say 1,000, then you get something like that in the end. You just do the same thing all over and all over and all over again, basically. So that's the second task. All right. I think I said what I should until now. Is there something else to add, maybe? Yeah, question?
Show the change here.
The
last one.
the with
change view direction.
change.
The one that says lab 3, change view.
Oh yeah. Oh yeah, that one I haven't showed, but yes, here I just pointed the camera in a slightly different direction than towards the origin. Can you see about where I pointed it? So the first one was always at the origin. So then I have my camera over here, right, pointing towards the origin of the coordinate system. Right. So here I have offset it slightly. So I point it here now, slightly to the right. So you can also play around with these matrices and see what happens once you set them up, because then you sort of get the idea about how, if you change the field of view, for example, if you in the perspective matrix, the aspect ratio. In this case, if you change what you point at, how will it look? So you get the idea of what that means. Any other questions? Okay, then I think we're set.
Men så det funkar, men tanken var ha en vektor som man var uppdaterad. Och så har vi kanske en lite annan. Och så ja, för exempel. Så är det den nya varje gamla plus